Okay, so last time we ended with this description of projective space. So you can think of projective space as lines in an plus 1, projective n space as lines in an plus 1. So in other words, you take kn plus 1 or an a sub kn plus 1, you remove the origin and you go mod this equivalence relation that two vectors are two n plus 1 tuples are equivalent if they are scalar multiple of each other. Yeah. So and we also saw that projective space you can from a fine space you can give a injective map to projective space, and there are many such injective maps, n plus 1 natural injective maps, where you send b1 to bn to sort of b1 to bi and 1 in the ith coordinate and bi plus 1 to n bn. Okay, so if in particular I is 0, then you can look at the complement, and complement is again a complement of this an. So you can think of an as a subset of pn. Yeah, and the complement is like pn minus 1. Yeah. So you can think of pn as a disjoint union of an and pn minus 1. And of course, pn you can also think of it as union of these ans. So if phi0 an is a subset of pn, and phi1 an is also going to be a subset of pn. They need not be disjoint, but their union is going to be whole of pn. Yeah. And by convention or by what I mean, no matter which definition you take, P0 is a point, and of course A0 is also a point, like by convention, let's say. Yeah. So this Pn you can write in a stratified way as an union disjoint union an minus 1 disjoint union an minus 2 up to a point. So this is where we sort of ended last time, and we want to give a topology to Pn. Yeah. So one way is to use this and the fact that Pn can be covered by these ans. Yeah, and on an we already have a Zariski topology, let's say. Yeah. So so we can induce a topology in Pn by saying that you can a subset U in Pn is open if and only if phi inverse U intersection an is open in an for all phi for all I. Yeah. So for all so this is sort of yeah. So one way of giving topology on some set on whose pieces we know or we know there is a natural topology. Yeah. So this is yeah. So this even quotient topology we sort of do something similar. Yeah. So it's in that philosophy. Another would be to give a quotient topology, and maybe even that is yeah. So even the quotient you have a topology on an plus 1, and yeah. So that I'll have to think. But I think the quotient topology is also this is also so this part I'll have to think whether the quotient topology from an plus 1 to Pn, since my topology is not that great, but I can't think offhand. But I think this should be okay. Yeah. So so there are two ways of giving topology on Pn. This is certainly okay. You cover Pn by these ans, copies of an, and then you say that things are open in Pn if you look at it locally, it's open. Yeah. And similarly, things are closed if so these two are equivalent. These, of course, yeah, because complement of closed is open and so on. So you either declare what are closed sets or what are open sets. So if you take this as your definition of topology, then of course by definition phi's are continuous maps. Yeah. So this is one way of defining topology on Pn. But remember, for An, the way we defined was that closed sets are algebraic subsets of An. So we also want to do that definition because we want to do algebraic geometry on Pn. So it will be nice to have some that kind of definition. So we'll go through. We'll do that. It uses what is called homogeneous ideals and graded rings and so on. So we'll get to it, and then we'll see that that definition is same as this definition. Yeah. So the two topologies are same. Okay. So we'll define what are algebraic subsets of Pn, and then we'll declare those are the closed subsets. Okay, so let's define first what is a so I suppose you know what's a homogeneous polynomial. So let f be a polynomial in k x naught to xn. So I mean Pn we think of it as we can also the first definition was you think of it as quotient of an plus 1. Yeah. So and to an plus 1 we can relate this this ring kx naught to x kx naught to xn. Yeah, homogeneous polynomial ring in n plus 1 variable. So that's where we sort of start. Yeah. So any point in Pn corresponds to a line in Kn plus 1, in An plus 1. So a polynomial in kx naught to xn is said to be homogeneous if every monomial, so f you can write it as sum of monomials. Yeah, so that is how we write a polynomial. And then each monomial has the same degree. Yeah. So if each monomial of has in f has the same degree, then we say that f is homogeneous. So for example, x naught plus x naught square plus x naught x1 plus xn square is a homogeneous polynomial in this ring. Yeah. So another way to characterize homogeneous ideal, at least when k is infinite, is that f f is homogeneous, then this part is always true, that f of lambda a naught to lambda n is lambda power d f a naught to f an for all lambda in k, and a naught to n in kn plus 1. And here d is the degree of f. And the converse will also hold if you assume k is infinite. So if you are working over an algebraically closed field, then this is not a problem. The only issue is finite field. So how do you? I guess this is straightforward. So I'll just go over it. So if f is some polynomial in x naught to xn, then you can write it like this. And it is homogeneous means ai will be non-zero only if this I naught plus, so I here is this vector I naught to in. Yeah. So so f will be homogeneous if ai is non-zero only if I naught plus I1 up to In is same as the degree of the polynomial. Yeah. So is equal to d, where d is the degree of the polynomial f. Okay. Okay. So so what is f lambda a naught to lambda n is just you just plug in lambda here, so you get lambda a naught I naught to lambda an in with the coefficient a sub I twiddle, and then you just factor out lambda power I naught to lambda power in, but I naught to in, so the only non-zero terms are when I naught plus I1 up to in is d, so you can factor out this lambda power d from each of these terms and you get this. Yeah. So the forward implication is straightforward. Even the backward implication is not that bad. Where did it go? Yeah. So if k is infinite, then we want to show that if this identity holds, then f must be homogeneous. So what you write is what one can do is write f as sum of homogeneous polynomials of various degrees. Yeah. So any polynomial you can write it as constant term plus all the degree 1 monomials, collect all the degree 1 monomials, then all degree 2 monomials up to degree d monomials. Yeah. So here fi is homogeneous of degree I. Then of course you plug in lambda a naught to lambda an, then what you get f of lambda a naught to lambda an is lambda power d. So fi's here on the right are homogeneous, so you can apply this and you'll get that this is lambda power d fd a naught to an, lambda power d minus 1 fd minus 1 a naught to an, and so on up to lambda f1 a naught to an plus the constant term will remain as it is. Yeah. So f lambda a naught to lambda an minus lambda power d f a naught to an, you'll get, so the first term will vanish and then the other terms will have these factors. Yeah. So of course, if one of these FDIs are non-zero, then of course you can find some, and k is an infinite field, then of course you can find, so you think of it as a polynomial in a naught to an and lambda. Yeah, so this is going to be some non-zero polynomial, and then of course you can find some a naught to n for which this polynomial does not vanish. Yeah, which will so which will contradict the fact that f of lambda a naught to lambda n is same as lambda power d f of a naught to n. So that means that all these fd minus 1, fd minus 2, etc., all this must be zero polynomial. If any one of them is non-zero, then the right hand side is a non-zero polynomial in, let's say, a naught to an and lambda, and that that will have any such non-zero polynomial has a will take a non-zero value for some vector, some lambda a naught. Okay, so that completes the proof of this straightforward lemma. So one consequence of this is that one consequence of this is that if f is a homogeneous polynomial and if you are in the setup of k an infinite field, then f vanishes at a naught to an, then it vanishes on the whole line passing through origin and that point a naught to n. Yeah, where a naught to n is some non-zero vector. It's not equal to 0. Okay. So if it is, if so, homogeneous, every homogeneous polynomial vanish at the other than the constant. So every non-constant homogeneous polynomial vanish at the origin. Yeah, because it has to have all degree terms. Okay. Okay, so so vanishing at one point means it vanishes on the whole line. So in some sense, it vanishes on the projective point, if you like. So now, this is the ring we want to work with, but we don't want to. So the idea is we want to we are looking for a zero set of ideals, and we want to define these zero set of ideals in projective space. Yeah. So of course, arbitrary ideals will define zero set in an plus 1, and we don't want to look at that. We want to look at zero set in Pn in some sense. Yeah, so we have to restrict our class of ideals we want to look at. Yeah, so those ideals are called homogeneous ideals. So let I be an ideal in kx not to xn. An ideal. Yeah, so this is written in a funny way. Yeah, sorry. An ideal I in kx not to xn is said to be homogeneous if I is generated by homogeneous polynomials. Yeah. So if you can find some homogeneous polynomials in I which generate the whole of I, then you say that I is homogeneous ideal. So another characterization of homogeneous ideal is that if you take any element f in I and write f as f0 plus f1 up to fd like we did here. So fi here f0 is the constant term of f1 is the uh, linear the degree 1 terms. So homogeneous degree 1 terms, f2 is homogeneous degree 2 term and so on. Then each of these fi's, each of these homogeneous pieces should belong to I. So f belongs to I implies all its homogeneous pieces belong to I. Then we said, and then I must be homogeneous. So of course the backward implication is clear. Yeah. So if this property holds, the second property holds, then I is indeed homogeneous because you can always find I is generated by some polynomials. I don't know, maybe we call it G1 to G or GM, and then you can look at homogeneous pieces of G1. So maybe G1 is G1 0 plus G1 D1. So these are, so maybe GI is GI 0, GI DI. So say GI has degree DI, so it will have DI homogeneous pieces. So these are homogeneous pieces, parts, homogeneous pieces, parts. Then by the hypothesis of the if part says that GI0 belongs to GIJ belongs to I and they are homogeneous. Yeah. So this implies GIJ are in I. And of course, I is generated by GIJs, and I is generated by GIJs. Because using GIJs, you can just take the sum, you get GI, and then GIs generate I. And each of these are homogeneous pieces, so by definition, it is a homogeneous ideal. Okay, any questions? Okay. For the other direction, so for the forward direction, one has to do some calculation. So suppose suppose I is a homogeneous ideal, so that means it is generated by homogeneous polynomial f1 to fm, and let's say fi has degree di, ideally in I, with fi of degree di. Okay. And let h be some element of I. Then we want to show that its homogeneous pieces are in, so h0, h1 up and so on, they are all in I. Yeah. So h is in I means you can write it as some linear combination, some you can write H as summation Gi Fi, where Gi's are some polynomials. Gi belongs to Kx naught to Xn for some G1 to Gm Kx naught to Xn. Okay, I don't know, something got stuck. K x naught to Xn. Okay. So now if you want to look at the constant term of H naught, so H naught, how does it look like? So you just have to look at the constant term of the right hand side. So it's Gi naught, Fi naught. Yeah, constant term of I of Gi and times the constant term of Fi, and you just sum them together and you get H naught. Yeah. But remember, Fi is homogeneous, okay, of degree Di. So its constant term will be 0 if Fi has degree different from 0. Yeah. So this right hand so this sum is basically Gi0 Fi, where for those for I equals 1 to m, but only those I such that Di is 0. Yeah, the degree you only have to look at those Di's, because so I such that Di is 0. So maybe I should write here instead of writing this ambiguous thing. I between 1 and m, 0 and m, 1 and m, yeah. I between 1 and m, and Di should be 0. Yeah, you take sum over these. So this left sum is same as this right sum. Yeah, because Fi 0 of when Di is 0, Fi 0 is same as Fi. And if Di is not 0, then anyway Fi 0 is 0. So that term vanishes on the left hand side. So we may not include it in the right hand side. And of course, this is some linear combination of Fi's. So some polynomial combination of Fi. So this of course belongs to I. Yeah. And the same thing you can do not just for constant, but any L. So if you have some L greater equal 0, then you look at degree L piece, a homogeneous degree L piece of H. So how do you capture the homogeneous degree L piece of H? Where H is this sum summation Gi Fi. So what you have to do is you have to look at so Fi, remember, is of degree Di. Yeah. So if you want degree L piece, then Di must be less equal L. Yeah. So we only have to look at again Di those polynomials Fi where Di is less equal L, and so I could be anything between 1 and m, but Di has to be less equal L. And so Fi is homogeneous of degree Di. Then you from Gi we only have to so if Fi is of degree Di homogeneous, and you are looking for homogeneous degree L piece of HL, then you have to multiply with homogeneous degree L minus Di piece of Gi. Then only you will get the homogeneous L piece. Yeah. So we are just collecting homogeneous L piece, and for that, so with Fi we'll have to multiply Gi L L degree homogeneous degree L minus Di piece of Gi. Yeah. So maybe I should here write that where maybe in this line itself, where Gi L minus Di is homogeneous degree L minus Di part of GI. Yeah, so GI, you can write it as the sum of various homogeneous degree pieces. So you just look at L minus DI piece. Yeah, and that sum is basically HL. So that again belongs to I. So we have proved that each HL is in I. Okay, so homogeneous ideals. There are two ways of thinking about it. One is that it's generated by homogeneous polynomials. Second is that if you can write it as sum of various homogeneous pieces of various degrees, then each homogeneous piece of a particular degree has to be in I for every F in I. Yeah. So let's see some examples. Yeah. So what is an example of a homogeneous ideal in Kx not to Xn? So of course, you just take a bunch of homogeneous polynomial and put it in there and consider the ideal generated by that. Yeah. So by the way, zero ideal is there, but you can look at x naught square x1 plus x2 cube, and maybe I don't know x2 square minus x1 square, something like this. So both are homogeneous polynomials. One is of degree 3 and one is of degree 2. So the ideal generated by these two is a homogeneous ideal. Yeah. And of course, this doesn't mean that every element in I is homogeneous. Yeah, you just take the sum of these two, then it's in I, and it's not homogeneous. But you take any element in this ideal I and look at its homogeneous pieces, then those should be in I. Okay, so that's what we observed. Another homogeneous ideal is x naught to xn. Yeah, so this is also a homogeneous ideal generated by. So this is a maximal ideal of kx naught to xn, and this is homogeneous. In fact, the only maximal ideal of kx naught to xn which is homogeneous is this ideal. Yeah, all the other maximal ideals of this ring are not homogeneous ideals. Okay. Any questions? Okay. So we'll look at zero set of these ideals, and those will be our algebraic sets. Yeah? So let's do that. Okay. So let I be an ideal in kx naught to xn, homogeneous ideal. Then note that if A is 0 to an, if you think of it as an element of an plus 1, it belongs to Zi if and only if lambda a naught to lambda n also belongs to Z of I. So I have been using B of I and Z of I interchangeably. Actually, I'm more used to B of I. I don't know why I chose Z of I. Okay. So so a naught to n belongs to Z of I if and only if lambda a naught to lambda n belongs to Z of I. Yeah, because I is going to be generated by some homogeneous polynomial, and if f is a homogeneous polynomial and a naught to an vanishes at so we have this corollary. Yeah, so f a naught to n is 0 if and only if f lambda a naught to lambda n is is 0 for all lambda in K. For all lambda in K. Okay, so if so you know x if it contains one point in an plus 1, it will contain the whole line joining the origin and that point. Yeah. So you take so you declare x to be zi minus the origin. So it look like a sort of a cone kind of thing. Yeah. If one point in an plus 1 is there, you connect join it to origin and you consider the line. The whole line is there. So this equivalence relation, so on Pn you have this equivalence relation and all this whole line will map to that point. So this x is going x, which is zi minus 0 modulo the equivalence relation is in Pn. Yeah. So this is our this is what we will call z of I. Yeah. In Pn. Yeah. So maybe this so x will also so this we will also denote it by z of I don't know. So I mean I'll drop this Pn later. So from the context it will be clear whether it is in Pn or an plus 1 or whatever. Yeah. So so it's the zero set of some homogeneous ideal. You remove the origin and consider the equivalence class. Or you can think of it as a point P, those points. So if you take a point in Pn, you just evaluate you evaluate it at any homogeneous polynomial in I, and it should be 0. Yeah. So those points are so X is made of those points, and you don't have to worry about which representative you choose. Okay. And Zi in an plus 1. So this is an plus 1. Yeah. So Zi in an plus 1. This is called the cone over X. Yeah. So this so while X is going to be something of dimension, let's say D, the cone over X is going to be of one dimension higher. It's going to be of dimension D plus 1. Okay. Because you know you have to so for each point in X there is actually a line in Cx. Yeah. So I mean it will become clear with this example if things are confusion. So suppose for instance you consider this I in K x0 x1 x2. So n is 2. Yeah. So this is A3 and P2. So we are in the set of, so this is coordinate ring of affine coordinate ring of A2, or if you like homogeneous coordinate ring of P2. Yeah. So zero set of I is going to be some one-dimensional object. If you are thinking in terms of projective, and if you are thinking in terms of affine, it's two-dimensional. Yeah. So think about, let's first think about it in terms of, yeah. So in terms of so in terms of affine geometry. So how does it look like? So this is x0 plus x1, x0 square plus x1 square minus x2 square. So this is indeed an equation of a cone. Yeah. So when x2 is 0, then of course, so I've drawn a real picture. Then of course x0 and x1 both should be 0, and you get one thing, something. But if x1 is non-zero, say let's say 1, then you get a circle, so something like this. Even if it is -1, you get the circle. So it does look like something like this. And as you vary x2, the radius of the circle changes. So you get this picture. Yeah. So this is the affine picture. So as you can see, if you take any point on this cone, then the whole line and connect it to the origin, then the whole line is on this cone. Yeah. But what is x? X is you just look, you throw away origin and then you sort of declare the whole line to be a point. So you can, so this any of these circles is basically x. Yeah. So if you depending upon which point you identify it with, it's like a circle. Yeah. So x is a circle in one chart, meaning if you think of so this in one chart means in one affine coordinate. Yeah, it does look like a circle. So x is a cone over this circle. So if you put x2 equals some constant, then you get a circle. If you put x naught equals some 1, then you get something else. So you get some hyperbola. So then it looks somewhat funny. But again, it will be a cone of, yeah, sort of a cone over a hyperbola. It's difficult to picture that, I suppose. Yeah. So I'm not very good with pictures, but it will look like again sort of a cone over a hyperbola if you vary x naught as well from. So if you put x naught equals 0, then of course you get two lines. But if you vary x naught, then you get some hyperbolas. So I don't know if someone is good with graphics, then they can sort of make it look like how this is a cone over various hyperbolas. Okay, so that's why this is a cone over something means that you just so you have some picture in A2 and you sort of in some plane and you make it you think of this A2 as a part of A3 and you just sort of connect it to the origin and draw all the lines. So that is what cone over something is. So that's a familiar term in topology as well. And that is what one does. Okay. So this is what one gets when you're looking at when you want to look at some algebraic subset of Pn. Yeah. So first thing to know, so as I was saying that if you have some homogeneous polynomial and P is a point in Pn, then Fp equals 0 or non-zero does not depend on the choice of the representation A naught to A. So the value of the function, if it is non-zero, will depend because it will be so if you have A naught to A and you multiply each of these vector by lambda, then the value of the function gets multiplied by lambda power the degree of the homogeneous polynomial. But whether it is 0 or non-zero does not really depend upon whether A naught to N is which representative you choose for this P, in A naught to N or some lambda times 2 A naught to 2 AN. Yeah. So so in that sense you can declare X to be so maybe I'll yeah. So here. Yeah. So a subset X in Pn is said to be an algebraic set if there exists a collection of homogeneous polynomial S such that X is and the set X is precisely those points in Pn such that Fp is 0 for all F in S. And Fp equals 0 makes sense. Yeah, it does not depend upon which representative you are choosing. 0 or non-zero is well defined. The value of Fp as such is not well defined if it is particularly if it is non-zero, but whether Fp is 0 is sort of well defined. So and that is called the zero set of S. Okay, where S is a collection of homogeneous polynomials. So these are algebraic subsets of Pn. Okay. So we have defined now what are algebraic subsets of Pn, and this will give us the topology. So before, is this clear, or you have some comments, questions? So we'll see more examples, I guess, yeah. But let me just complete this set of definition for algebraic sets. So remember, like in affine case, zero set of some collection of polynomials is same as zero set of the ideal generated by those polynomials. Yeah. So we just look at ideals instead of arbitrary subsets of the polynomial. So here, instead of arbitrary, since we are looking at zero set of homogeneous polynomials, we should look at homogeneous ideals. Yeah. So if I is a homogeneous ideal of kx naught to xn, then the zero set of I is defined to be p such that those points in Pn such that fp is 0 for every homogeneous polynomial in I. Yeah. So if I is generated by, say, f1 to fn, where f1 to fn is homogeneous, then it's enough to look at zero set of those homogeneous polynomials. So instead of vanishing of all homogeneous polynomial in I, it's enough to look at vanishing of those homogeneous polynomials. And again, you have that zero set of I plus j. If you take two homogeneous ideals and consider the ideal generated, smallest ideal containing both these homogeneous ideal, then that's again homogeneous, right? Because I is generated by a list of homogeneous polynomial, j is generated by a list of homogeneous polynomial. Then of course, I plus j is generated by this union of these two lists. Yeah? So it's a homogeneous polynomial, and the zero set of that is same as zero set of I intersection zero set of j. So the proof of this is same as in the affine case. Yeah. So I'll not repeat it. You just look at that. Similarly, if you have two homogeneous ideals, I and j are homogeneous ideals, then their intersection is homogeneous. Yeah, so how do you prove that? So then here you can use the other characterization. Yeah, so suppose f belongs to I intersection j, then each of its homogeneous pieces belongs to both. So it belongs to both I and j, because f belongs to both I and j, and hence each of its homogeneous pieces belongs to I intersection j, and hence I intersection j is a homogeneous ideal. And then the zero set of I intersection j is zero set of I union zero set of j. So that lemma, so we are using that lemma, which gave you another characterization of homogeneous ideals. Okay. And again, if you have a subset of Pn, then you can define the ideal of definition of X as well in Kx naught to Xn. So this, okay, so something is already wrong here. So K X naught to Xn. Okay. So you consider those homogeneous polynomial in Kx naught to Xn such that it vanishes at every point of X. Yeah. And consider the ideal generated by these homogeneous polynomials. So of course, by definition, Ix is a homogeneous ideal. And so this is the ideal of definition of X. If, yeah, so if you look at, so if X is, so if you look at the zero set of this ideal, you'll get X if X were an algebraic set. Otherwise, what you'll get is its closure if we define Zariski topology as to be. Yeah, so maybe, so maybe I'll write it after defining this. Yeah, so Zariski topology on X or in Pn. So on maybe on Pn is that closed subsets are algebraic subsets of Pn, and on X, where X is some algebraic subset of Pn, then you say that Zariski topology on X is those is given by closed sets are algebraic subsets of X. Okay. So when X is Pn, you get an algebraic subset. You get a Zariski topology on Pn. So these properties. So for instance, if you take so one has to check that this is again a Zariski topology. Yeah. So but you remember we sort of use this property, this statement, this star, and to say that finite union of closed sets are closed and arbitrary intersection. So here we have done two ideals for some, but you can do arbitrary number of ideals and take this on. Yeah, and this identity still works, the first identity. So these helps us show that this is indeed a topology. Of course, Pn. How do you get so Z of the zero ideal is whole of Pn, and Z of let's say the Z of the whole ring is the empty set. So that will tell you that this is a topology. Okay, and what I want. Yeah.
Sir, when you are saying that P belongs to Pn,
yeah.
So P point belongs to X and Fp is equal to 0. So you mean that you are taking a representative of P in An and
yeah, exactly. Yeah. So okay, so maybe here, yeah, and so this Fp means Fp by definition is or Fp equals 0. Maybe since Fp may not be well defined, Fp equals 0 means F A naught to An equals 0. Okay. These two are same. Yeah. So the point is, it doesn't matter which representative you choose. Otherwise, you can't plug in. Yeah. So it doesn't make sense to plug in P, because P is some equivalence class. It's not really a element of Kn plus 1. Yeah. Is this clear now?
yes.
Yes. So we are just taking some representative of the point P. P consists of so if you're thinking in terms of equivalence classes, it consists of a line in Kn plus 1. It is basically a line in Kn plus 1. So you can't plug that in, but any point on that line you can take, any non-zero point. And it doesn't matter which non-zero point. So the value, this F A naught to An may, if it is non-zero, then its definition changes. I mean, its value changes as you take different representative, but 0 is okay. Any other questions or comments? Okay. So okay, so maybe, yeah. So you can define, so ideal of definition is there. Zariski topology, you define it to be closed subsets of algebraic sets. And then you can check, so then what will happen is, if you take Z of I of X, then this is X closure in Zariski topology. Yeah. So these proofs are same like in the affine case. So nothing different. Yeah. Just that instead of ideal, you have to replace it by homogeneous ideal. So and points, you have to deal with equivalence classes and so on. Yeah. So you just verify it. Maybe I'll put it as some of them as homework, so that you get some feel about it. Okay. So maybe in 2 minutes we'll work out some what are algebraic subsets of P1. Yeah. So algebraic subsets. So of course, one is the empty set, and P1 are there. What else? So so P1, remember, is element of P1 looks like A naught A1, where this A naught A1 is not a zero vector. Yeah, a class of this. Yeah. So so one, if you want to know what are algebraic subsets of P1, one can ask whether one this is a point in P1. Yeah. So is this algebraic subset? So this should be a point, should be an algebraic subset, right? Like in the affine space. So is this an algebraic subset? So we want to know whether this is an algebraic subset or not. So we'll have to find a homogeneous polynomial. So P1 so if you are looking at P1, um, um, and you want to know some subset of P1 is an algebraic subset, so one has to look at this homogeneous ring x naught x1, and we this polynomial ring, and we want to find ideal I in kx naught to x kx naught x1 I homogeneous, such that Zi is precisely A naught E1. Yeah. So what should be our I? So maybe first we look for one homogeneous polynomial which vanishes at A0, A1, and then maybe we'll see if that one polynomial is enough or not. Yeah. So A naught A1 is some element of A2. If you think, I mean, you think of this as A2. Yeah. So if you want a polynomial which vanishes at so if you consider a polynomial which vanishes at A naught A1, so they look like x naught minus A naught, x1 minus A1. Yeah. The whole so every polynomial which vanishes at A naught A1 is actually inside this. Yeah, because the ideal of definition of this point in A2 is precisely this maximal ideal. But of course, will have to find a homogeneous polynomial. So which is a homogeneous polynomial in this ideal? So maybe some homogeneous polynomial if we take. So of course 0 is there, but don't give me that. What's another homogeneous polynomial?
E naught x1 minus a1 x naught.
Yeah. So here you can just manipulate here and see that a naught. This is x1. So you multiply this. So you basically wants to cancel this constant term in some sense. Yeah. So you multiply the second one by a naught and first one by a1 and take the difference. So a naught x1 minus a1 x naught. And then the constant term vanishes. And this, let's call it f. So this is a homogeneous polynomial. Yeah. And this belongs to this. And z of f is precisely I mean, if you are looking at in A2, it is the line which connects origin and A naught A1. Yeah. So this is in A2. So if this is this, then this is A naught x1 minus A1 x naught equals 0. Yeah. So I mean, it's is a linear guy, so it is 0 locus is a line, and of course both origin and these 2 points are on that line, and there is only one line joining these two. Yeah, so is precisely this line, and hence as this line, let's call this L. So it's this L, and hence Zi as ZF as in P1 is just this point in T1. Yeah. So you can take I to be the ideal generated by F. Yeah. So we see that a point in P1 is indeed closed, and then by our topology, we know that any finite collection of points is in P1 is actually closed. Yeah, because finite union of closed sets are closed. And that's it. So so if you take any infinite set, then it's not going to be closed. Yeah, that's also there. So so that also you can prove. Okay, so here the topology on P1 is cofinite topology. The topology on P1 is cofinite topology. Okay. Okay, so maybe next time we'll talk more about it. So this is a good place to stop. So let's stop here.